Hello and welcome to Technology Update. It's the end of October and the nights are closing in here in Moscow. But luckily for us, the summer hasn't finished everywhere, so we thought we'd pack our bags and go in search of the sun.
Winter's knocking at Moscow's door, but we're not ready to don our long johns just yet. So we travelled to Europe to soak up some rays, imbibe the culture, and see what's going on in the world of technology. France was Europe's largest exporter of electricity last year. But despite this abundance in power, the country is still looking for new energy sources and even hopes to bring the power that drives the sun down to earth. There's a lot of energy in France, and I'm not just talking about the street dancers. The country ranks second in the world in terms of nuclear power stations. But with growing environmental and safety concerns, the sun may be setting on nuclear energy as we know it. So ministers from around the world have come to discuss a possible shift away from nuclear fission. There are currently 185 nuclear power plants in Europe, and another 17 are on the way. France has almost a third of the total with 58 plants, producing 78% of the country's energy needs. All these stations have produced well over 1 million cubic metres of radioactive waste, 90% of which is stored in 3 facilities. This is where nuclear fusion comes in. But what's the difference? Nuclear fission isn't normally found in nature. It's the process by which heavy elements split to form lighter elements and has been created by mankind to make power stations and nuclear bombs. In a typical reaction, a neutron hits a uranium isotope, which causes it to destabilize and split into smaller elements and neutrons, giving off energy. Unfortunately, it also produces large amounts of radioactive waste, which is incredibly hard to dispose of safely. Nuclear fusion, on the other hand, is nature's atomic power. You just have to look at the sun or the stars to see it in action. In this reaction, hydrogen isotopes, in this case tritium and deuterium, combine to form a heavier isotope helium, a single neutron, and lots of energy. But perhaps most importantly, fusion gives off hardly any radioactive waste.
The idea of ITER was first discussed at an international forum in Washington in 1975. Together with the leader of the US thermonuclear program, we gave a report on things we could do together and on ways to do them. Back in 1975, we said we should work on what is known today as a technological platform. This was ITER. This is what we said back in 1975, and all the work after that basically followed this plan.
Velikhov suggested that General Secretary Gorbachev bring it up at the Geneva Superpower Summit in 1985. He discussed it with President Reagan, and the International Thermonuclear Experimental Reactor Project, or ITER, was born. Europe, or France in particular, was already looking to diversify its energy sources and joined the project along with Japan. In 2006, the ITER agreement to build, run and decommission was signed, and ground was finally broken in 2007. Construction is now in full swing and gathering momentum every day. ITER is also Latin for the way, symbolising the weight energy. Located in Cadarache in the south of France, it's one of the most ambitious international scientific collaborations ever undertaken. The EU, India, Japan, China, Russia, South Korea and the US, representing over 1/2 of the world's population, are all taking part in the project to make the holy grail of energy production a reality. But nuclear fusion won't come easy. Even the groundwork for the project is a feat in itself. The ITER site is the size of 60 football pitches, making it one of the largest man-made levelled surfaces in the world. The access roads from the ports have all been reinforced to support the weight of the deliveries, and 5,000 people are expected to be working on the site during the peak of construction. As the host country, France is responsible for a lot of the infrastructure, but the sheer size of the project is too much for one country alone.
Since this is an international project, it's very important to make sure we're all on the same page. Different countries will be providing different components, and it's important that all the components are supplied at the right time. Compatibility issues need to be taken care of.
Nature has none of these problems and cracked fusion a long time ago. The temperature at the sun's core is 15 million degrees centigrade. This, combined with its huge mass and density, create the perfect conditions for fusion. So perfect, in fact, that it fuses 620 million tons of hydrogen every second. Once construction is complete, the real fun starts. At the heart of the entire complex is this fusion reactor, which will recreate the conditions in the centre of the Sun here on Earth. Deuterium and tritium are equally charged, so to overcome their natural repulsion, which happens so easily in the Sun, they need to be heated to over 150 million degrees in a vacuum. At this temperature they form a plasma, which is confined in a toroidal, or donut shape to you and me, magnetic field. An electric current is run through the plasma to help heat it, and the walls of the chamber have to be built to withstand the intense heat and vacuum conditions. And this magical device that can create stars is called a tokamak, but it's not a new invention. Tokamak is a Russian acronym for toroidal chamber with magnetic coils, and it was created in Russia over 60 years ago. Many of the people I'd spoken to mentioned a young Red Army soldier when I asked them about the history of nuclear fusion. So I went to the State Library in Moscow to find out more. I was intrigued by this mysterious figure who, despite having received very little formal education before the outbreak of the Second World War, had developed a passion and a talent for nuclear physics. Oleg Lavrentiev was the first person who proposed confining plasma in an electrostatic field. In 1950 he wrote his ideas in a letter to Stalin, but never received a reply. But a second letter addressed to the Central Committee caused quite a stir, and he was invited to Moscow to discuss his ideas with Soviet physicists Andrei Sakharov and Igor Tamm, and they were impressed by his originality and boldness. Sakharov recommended that work on nuclear fusion get started straight away, but refined Lavrentiev's idea using a circular magnetic field instead. Physicist Igor Kurchatov gave a talk in England where he revealed the Soviet Union's novel approach and progress. The world was impressed. The UK declassified its nuclear fusion research, and international cooperation began in earnest. The first magnetic plasma containment device, the T1, was created in 1957. The T3, which both Sakharov and Tamm had been working on, was completed in 1968. It achieved record temperature levels and plasma confinement times, and the tokamak was to become the dominant concept in fusion research. After this, tokamaks began to spring up all over the world. Some of the most notable include the Joint European Torus, or JET, in the UK, which achieved the first controlled release of fusion power and holds the record for the most power produced. This tokamak is currently being used to test a wall lining for ITER. Japan's JT60, which holds the record for the highest plasma, time, density and temperature ratio, and the TFTI in America, which managed to heat the plasma to a mind-blowing 510 million degrees C. Despite these advances, no tokamak has ever achieved the long-sought break-even point, where a device releases the same amount of energy as is used to start the reaction.
ITER is not a thermonuclear power plant, it's an experimental reactor. Its purpose is to show everyone that all the major technological and physical problems have been solved, and that thermonuclear energy is now available as a source of electricity for industrial needs.
There are alternatives to the tokamak. The Stellarator was invented in 1950 in the US and doesn't run a current through the plasma, making it easier to operate. However, any deviation from the complex geometric form results in a significant reduction in plasma containment characteristics. But a lot of progress has been made in Germany in recent years with the Wendelstein 7X. Inertial confinement fusion uses dozens of high-powered lasers to heat a compressed hydrogen fuel pellet and ignite a fusion reaction. Although exciting from a theoretical point of view, it can be tricky to extract power from this method.
The tokamak turned out to be the most practical plasma confinement system. And the fact that these days, every decent university or laboratory has its own tokamak proves it.
The first ever tokamak, the T1, was built right here at the Kurchatowski Institute in Moscow. The institute is named after Igor Kurchatov. The Russian domestic ITER agency is also based here, managing all aspects of the country's participation in the ITER project. The institute is now home to the T1's distant descendant, the T10, which was built almost 40 years ago and is the largest tokamak currently operating in Russia. The T10 has generated around 90,000 plasma pulses, which is way over its original designation. Despite its age, the Old Faithful still has a place in today's research and plays an important part in testing how plasma interacts with electromagnetic waves for ITER.
Firstly, we'll use this tokamak to test out new technologies. Once they are tested, we can apply them on a bigger scale. Secondly, we also use it to develop new diagnostic methods. This is not an easy task because, in actual fact, many of these diagnostic tools do not yet exist, and we'll use ITER to develop them. And some of these diagnostic tools will be developed here, at our facility.
The tokamak is located just behind these walls, and take it from me, it's quite something to see the plasma with your naked eye. But if you want to be able to control it, you have to it. And this is why they have this beam generator. The generator sends a beam of neutral particles through the plasma, which causes it to undergo a series of spectral changes. The beam then comes out of the plasma and is sent through this fibre optic cable. The constant beam is given a frame rate of about 250 per second with this shutter. The beam then goes through this box and through a series of lenses and is finally picked up by the spectrometer just through there. The spectrometer then sends all this information to a computer which does the number crunching to calculate the spectral properties of the beam. And it is these properties that let you calculate the heat and the concentration of the plasma. The electric field strength and rotation speed of the plasma can also be worked out from these measurements. These four factors are the most important plasma characteristics that need to be monitored, and a beefed up version of this laser system will eventually be fitted in the ITER reactor. But one diagnostic system on its own is far from enough. Every aspect of the reactor must be monitored closely.
There are different types of diagnostics. There are physical diagnostics, there are technological diagnostics, and then there are safety diagnostics that give us a clear picture of the things happening inside the reactor.
Given the experimental nature of ITER, the reactor will have around 45 diagnostic systems, 9 of which have been developed here in Russia, 3 in the Kurchatowski Institute, 3 in the IOFA Institute, and 3 in the Trinity Research Institute. The diagnostic systems range from lasers, X-rays and neutron cameras to impurity monitors, particle spectrometers and radiation bolometers. Unfortunately, we can't cover them all, but we managed to check out a few. The Kurchatowski Institute is also working on this high field side reflectometry system, which sends microwaves through the reactor and uses the extent to which they're reflected to gauge the density and therefore the stability of the plasma. A wide range of frequencies are used, which allows them to take a cross-section and see the density distribution within the plasma. The system is tested using this full-scale mock-up of the waveguide and tokamak wall, but the main challenge is sending different wave frequencies down the same guide without distorting them.
This diagnostic technology, the way it is meant to be applied at ITER, has never been used with a tokamak. So we decided to start by installing diagnostic sensors inside the T10. And now we have collected a full range of diagnostic results.
This is a full-scale replica of the IOFA Institute's Divertor-Thompson scattering system for ITER. The 6-ton device will be located just 1.5 meters away from the hot plasma. The business end of the instrument has only a 2-centimeter gap in the tokamak wall to work with. The divertor helps maintain the purity of the plasma and plays an important role in ensuring the safe operation of the tokamak. This vertical gamma ray camera registers the gamma radiation produced during the reaction. This information in turn can be used to measure the confinement of the alpha or helium particles generated during fusion. Alpha particles play a crucial role in producing a burning plasma, which is a self-sustaining reaction and requires little, if any, auxiliary heating power. The Institute is also building this neutral particle analyzer to measure tritium and deuterium concentrations. It picks up the atoms in the tokamak, ionizes them, and uses their mass and energy to identify the 2 hydrogen isotopes. Any deviation from a 1-to-1 ratio would result in a serious drop in the efficiency of the reactor. This information allows the fuel levels to be adjusted accordingly.
Russia has been put in charge of supplying this diagnostic system. Basically, that's because we've been leaders in the application of these diagnostics in thermonuclear installations for a number of decades now. We've produced dozens of instruments operating on this principle and supplied them to our foreign partners.
The Efremov Institute is also located in St. Petersburg and is heavily involved in all aspects of ITER, So I went down to their industrial labs to see what they were up to. Maxime here is currently working on plasma ignition and cut-off systems for the ITER reactor. The igniters generate the huge electrical currents required to heat the plasma. They're also developing these pyro breakers to protect the superconducting magnets from overheating. If this happens, a small explosive charge in the pyro breaker detonates, causing a small aluminium ring to expand and complete a bypass circuit, which discharges the excess current in less than 20 microseconds, kind of like a giant fuse.
We have a range of key technologies being developed for ITER that must be supplied on time. Some of them are needed to ensure the experiment safety. Among them are technologies related to the magnetic system, the vacuum chamber, the power system, and some chamber elements.
This panel is part of the inside wall of the tokamak. It's made up of lots of little tiles like this one. Each tile consists of a layer of tungsten, copper and bronze, and the inside wall will have over 1 million of them, and 600,000 will be made here in Russia. Europe and Japan also make these panels, and they send them here to be tested in this chamber. The chamber can heat them to 3,000 degrees C, but it only tests them to 1,500, which is the exact same temperature as inside the tokamak. The inside wall of the reactor represents an immense engineering challenge. The heat it's subjected to is the equivalent of 100,000 light bulbs shining on 1 square metre, while the forces exerted by the magnets could be compared to the weight of 50 lorries. And if this weren't enough, the neutron bombardment slowly degrades the structural integrity of the wall. This testing chamber contains an electron beam which imitates the heat load on the wall to ensure it's capable of dissipating all this heat over a relatively small area without fracturing. So how can tungsten with a melting point of 3,500 degrees withstand temperatures of over 100 million? The trick is, most of the particles are held in the plasma. Only a few of them can escape the magnetic field and reach the first wall of the tokamak. The density of the particles drops significantly, which means that the effective temperature the wall is subjected to is also lowered. The water cooling the wall is heated, producing steam, which drives a turbine to produce electricity.
This is a complicated task because we have to combine different materials into a single structure which should be able to operate for a decade or so, being exposed to aggressive plasma. We draw from Soviet and Russian researchers' experience with modern materials, for example, in high-energy laser mirrors, rocket nozzles, re-entry vehicle fairings and thermal protection, high-energy radars, etc. This is why Russia was able to achieve excellent results in this area.
A lot of the manufacturing techniques have had to be adapted especially for ITER. This laser welding machine is used to create seamless joints in ITER's stainless steel water cooling system. Unlike traditional welding techniques, there are no impurities in the weld or splashes of molten metal. More on ITER after the break.
A lot of the work for ITER has been carried out here in St. Petersburg, and what better place to come than the IOFA Institute, which is the birthplace of nuclear physics in Russia. It is also home to the country's newest tokamak, the Globus M.
Kurchatov himself worked as a senior researcher at the IOFA Institute before moving to Moscow to head his own lab. As well as developing many diagnostic systems for ITER, the Institute has also built a tokamak of its own. It uses a device to study plasma behaviour as well as test out auxiliary heating systems, but it's not like any tokamak we've seen before. The Globus M is a spherical tokamak. It's also the newest in Russia and was built entirely in St. Petersburg. It's more compact than traditional tokamaks, so the magnets are located much closer to the plasma, which greatly reduces the amount of energy required to confine it. The shape of the chamber also makes the plasma inherently more stable, and an increase in efficiency is achieved by holding the plasma much more centrally. Despite the magnetic fields being generally weaker in this type of tokamak, making it harder to reach the required plasma density, it's certainly not without its uses.
As far as the energy industry is concerned, Researchers are currently designing what's called a hybrid reactor. That's a tokamak, or a spherical tokamak in our case, is used as a source of fast neutrons. Unlike, say, ITER, there's no self-sustaining reaction, and those fast neutrons are used to irradiate spent or unspent nuclear fuel, like what's normally used in classic fission reactors.
Russia isn't just providing a lot of the technology for ITER, a lot of the manufacturing is being carried out here as well. One of the country's specialities is superconductors, so that's why it's joined forces with 5 other countries to produce coils for ITER's toroidal and poroidal magnetic systems. Russia will provide a total of 73 spools of superconducting magnetic cable for ITER, each with a length of over 800 meters.
We are very pleased that our superconductors have extremely stable characteristics. Our parameters don't get very high and then fall very low. They are high and stable from sample to sample. This means our production method is stable.
There are many stages to the manufacturing process. The thin superconducting wires are produced at the Chapetsk mechanical factory and are then sent 750 miles here to Podolsk, where they are cleaned and coated in chrome. The wires are then wound to produce strands, which in turn are wound 5 times to produce a cable 4 centimeters thick. It's then wrapped in a steel jacket and compressed. The cable is loaded onto an 8.5-ton spool for transportation to ITER. Most of the magnets will be assembled in ITER's giant magnet assembly facility, apart from one which will be manufactured in Russia. All in all, ITER will have 18 superconducting toroidal field and 6 poloidal field coils, a central solenoid, and a set of correction cores that confine, shape and control the plasma inside the vacuum vessel. Nizhny Novgorod is an ancient Russian city, not only renowned for its picturesque beauty and rich history, but its reputation for scientific research and manufacturing is known far outside Russia's borders. At the end of August this year, ITER General Director Osamu Motojima visited Nizhny Novgorod to inspect JICOM's production facility. JICOM is responsible for producing 9 out of the 24 gyrotrons in ITER. Gyrotrons were invented in Russia in 1964 in what is now called the Nizhny Novgorod Institute of Applied Physics. They're now used in the vast majority of tokamaks throughout the world, as heating the plasma without them would be next to impossible. ITER's 24 gyrotrons will be located in a separate building 150 meters away from the reactor. The electromagnetic waves they produce will be sent via long waveguides into the reactor, helping heat the plasma to the temperature necessary for fusion.
We see ITER as a regular customer, since we've agreed to supply it with 9 gyrotrons by the year 2020. They're a regular customer, but we also hope to be able to sell 2 or